we have seen the finite volume method for discretizing the governing equation. So, now let us do a tutorial on this. We will go back to the triangular duct problem, and in this tutorial we will try to derive the equations for the 9 points which we have seen earlier. So, we will start with our equilateral triangle. Of side A here, and we divide this into 3 parts. So, we have 9 triangles here, bit bigger, but otherwise they are all supposed to be of the same length like this, and we can put our origin here. This is x and y. We will identify the centroids of each of these, and let us call this by the numbers: cell number 1, cell number 2, 3, 4, 5, 6, 7, 8 and 9. We would like to discretize this equation with this boundary condition for each of the cells and get 7 algebraic equations, 9 algebraic equations. So, this is the tutorial, and let us get started. We have already seen how this is going to be done for how this can be done for cell number 7, but let us start with cell number 1. Okay, so this cell has we can say that this is the total length is 3 times A, therefore the side of each of the small triangles is A. So, this is A and A. Similarly, this is A here like this. So, for this cell, this is cell 1, our origin is here, and this is 60 degrees. So, we can say that this length is A here. The midpoint, this is at distance of A by 2, and this whole height is square root of 3 by 2 times A, and this height is h by 3, where this is h. Okay. So, from this we can say that xc1, that is the x coordinate of the centroid for the cell 1, is equal to A by 2, this distance, and yc1 is h by 3, where h is this. So, square root of 3 by 2 times A divided by 3 is A by 2 square root 3, and we can define, there are 3 sides to this. So, the midpoints of each of these we would like to define. Okay. So, we can say that we can always go in the counterclockwise direction for any given triangle, and we can always start with the horizontal side. Each of these has a horizontal side. So, for example, this cell, this is a horizontal side. So, when we come to description of the sides here, so we have side 1, side 2, side 3, because we are going in the counterclockwise direction. And when you look at cell 3 here, then this is cell 1 and this is side 1, this is side 2 and this is side 3. So, for each triangle, for the sake of convenience, we go in the counterclockwise direction, starting with the horizontal face cell as side 1, and then we can go to the next one and then next one like this. And that allows us to fix the coordinate directions of the midpoints for each of the cells. So, this is a heuristic way of doing this, and so we can say that x m1, that is, this is side 1, side 2 and side 3. Okay. So, that is why we call it as xm1 is a by 2 and xm2 ym1 is 0. Okay. Similarly, this is xm2 and xm2 is halfway between these. So, it is exactly at this. So, this is 3 by 4 a and ym2 is half height of this. So, that is h by 2. So, that is square root of 3 by 4 a, and this is the midpoint of the third side xm3, and this is at an x distance of 1/4 of a, and y distance is at the same height as this. So, that is square root of 3 by 4 a. So, this is the geometric information. In addition to that, we can, let us call this as P, Q, R, the 3 vertices, and we can also put here XP, okay, X and Y of the 3 vertices. For P it is 0 0, that is the origin, and for point Q the distance is a here and y is 0, and for R this is x of R is a by 2 and y of R is square root of 3 by 2 a. Okay. And finally, we want to have the area of cell 1. This is half into base into height. So, that is half 3a, no, this is a here and height is 3 by 2 a. This is 3 by 2 a, square root of 3 by 2 a. So, this is square root of 3 by 4 a square. Okay. So, we have for this particular cell, we have all the geometric information directly from the location of this cell with respect to everything else. And we can now look at the discretization of this, which we can write as nx dou w by dou x plus ny dou w by dou y times L for cell I, for side I over all the 3 faces. So, we can write this as over PQ plus QR plus RP, okay, equal to the constant C times the area, which is square root of 3 by 4 A square. Okay, so now we need to evaluate the Nx, Ny and all these things. So let's start with, for side okay. So let's do this systematically. So we can say that in the form of a table we have side PQ, QR and RP. So for each of these we can write Nx, Ny, dou W by dou X and dou W by dou Y. So that it will be easy for us to evaluate these terms and then multiply by the length and all that. So if we come to this PQ, Nx is 0 and Ny is minus 1 for the midpoint here, and here Nx is square root of 3 by 2 and Ny is minus half, no, Ny is plus half, and here it's like this. So for RP this is minus square root of 3 by 2 and plus half. So the three normals are like this. Okay, so here this is Nx, Ny, Nx, Ny, so Nx is negative and equal to this. And dou W by dou X, since this is 0 here, we don't need to evaluate this. And dou W by dou Y at this point here. So we need to estimate this in terms of known quantities. And when you consider this triangle here, what are the known quantities or to be known quantities? This W at this point is being evaluated, and it's also given that W at this point is 0. But unfortunately in the equation we don't need the W at this point, we need to have the gradient dou W by dou Y at this point. So we can estimate the gradient dou W by dou Y at this point roughly as W1 minus this velocity, which is 0, divided by this distance, and that distance is yc1 minus ym1, and ym1 is 0. You can see that ym1 is 0. So we can write the gradient here as w1 minus 0 divided by yc1 minus ym1. Okay. Now we come to side RQ, and we can evaluate the dou W by dou X at this point as W2 minus W1 divided by XC2 minus XC1. So W2 minus W1 divided by XC2 minus XC1 based on the two nearest values that we have here. And we also need dou W by dou Y, and that will be this value minus this value divided by the vertical distance. So that is W2 minus W1 divided by YC2 minus YC1. Now you come to this one here, this side here, and Here dou w by dou x is to be estimated from this and the immediate neighbor. There is no immediate neighbor because it is a wall, and we know that the w velocity at this wall is 0. So, we are bringing in the information of the boundary condition here. So, we can say that this is equal to w1 minus 0 divided by xc1 minus xm3, that is the third point here, because that is the third phase. And similarly, this is w1 minus 0 divided by yc1 minus ym3. Okay, so in order to now discretize this over this cell, we need to multiply this by this and this by this, and then this by this and this by this, and then this by this and this by this, and then add up all of them and put that equal to this. So, let us see, we can substitute the values here. So, that gives us minus w1, we have minus 1 times w1 divided by ym1 is 0, okay, ym1 is 0, and yc1 is a by so this is what we are getting from this, plus square root of 3 by 2 times w2 minus w1 and xc2 minus xe1. So, this is xc2 is this, and xc1 is xc2, this is at distance of a here, and this is a by 2. So, the distance between the two is a by 2, a minus a by 2, and here we have plus half into w2 minus w1 divided by the vertical distance. This is at h by 3 from the top, and this is h by 3 from the bottom. So, this is 2h by 3. So, this must be h by 3. This is 2h by 3 from the top of this, and the top is the same as this. So, this is h by 3 from the bottom. So, this distance here is h by 3, and so this is, and h itself is square root of 3 by 2. Okay, so this is what we have from this, and here we have minus square root of 3 by 2 times w1 divided by xc1 is a by 2 and xm3 is a by 4. So, the difference is a by 4. Okay, plus half times w1 by yc1 is h by 3 and ym3 is square root of 3 by 4a is what we have here. So, this is h is 3 by square root of 3 by 2 by h times 1 by 3 minus and this whole thing here is equal to constant times the area, which is 3 by 4 a square. Okay, so this is the equation here, and in this equation a is given, so everything else is all the w's are coming with coefficients. So let us just add up all the things and get an equation for cell 1. So from the, we can say W1 times, in the first term we have, this is in the denominator, so this goes as minus, so we can divide by a here because a is occurring in all of these, is what we have, and here we have a by 2, and that goes into the numerator, and so that time this cancels out, minus square root of 3, and here again we have there is a mistake here. So this is 2 square root 3 will be going in the numerator. So this is minus 2 square root 3 divided by 2 is from here, and here we have 4 going here, so that becomes minus 2 square root 3. And here we have okay, so this is a by 3 and this is a, so this is minus 2a by 3. So this will be 1/3 of 1 by square root of 3. Two a by 3, so 2 cancel out, so you get a by square root 3 minus a by square root 3, and so this is minus okay, so this is all for W1, and for W2 we have so we have 1 by 2 here, so that goes as square root of 3, and here we have 2 root 3, so this is plus root 3 here, and that is all there is for W2, and there is nothing else. So this is equal to so we can take the a to this side and we can evaluate all this. So this is okay, 2.5, 3.5, 4.5, 6.5. So I am getting minus 6.5 square root of 3 W1 plus 2 square root of 3 W2 equal to square root of 3 by 4 times a cube times c. So this is the equation that we have for cell 1. So let us also fill this table for cell 2 and then we can do this at leisure. So for cell 2 is this, So, as per this figure, cell 2 has immediate top neighbor of 6, left neighbor of 1 and right neighbor of 3, and these are the centroids for each of these, and this is our coordinate origin. So, just as before, we can start with this as P, Q and R. We start with the horizontal thing, go in the counterclockwise direction and then come back up like this. So, we can say that for this space xc and yc, xc is at a distance of a here and yc is at a distance of 2/3 of h. So, 2/3 of h is square root of 3/2 times a. Okay. So, this is equal to square root of 3a. Sorry. So, this is now this is our x m1. So, that is this point here and that is at a here, and y m1, this is this height. So, that is h. So, it is square root of 3/2 h. This is our m2. So, that is the second point, midpoint for the side QR. So, that is xm2 is at this distance, which is a/4 or 3a/4, and height is half of this. So, ym2 is half height is square root of 3/4a, and this is our xm3 is this distance plus half of a. So, this is 3/2a, and ym3 is at the same height as this. So, that is square root of 3/4a. So, we have important coordinates of important points here, and we can similarly write down the coordinates of the vertices, and the area is already known. So, let us go and side and then nx, ny, dou w by dou x, dou w by dou y. Okay. So, now for the side starting with PQ, nx is 0 and ny is 1, and here and so dou w by dou x does not matter, and dou w by dou y is w6 minus w2 divided by yc6 minus yc2. For the side QR, okay, please note that this QR is for this cell. Okay. So, for this QR we have, this is n. So, nx is minus square root of 3/2 and ny is minus half, and dou w by dou x is this minus this divided by this vertical horizontal distance. So, that is w2 minus w1 divided by xc2 minus xc1, and dou w by dou y is w2 minus w1 divided by yc2 minus yc1. And finally, for the side RP, we have n going out like this. So, this is nx and ny. So, nx is square root of 3 by 2 and ny is minus half, and dou w by dou x is based on these two things. So, this is cell 3. So, w3 minus w2 divided by xc3 minus xc2, and similarly dou w by dou y is w3 minus w2 divided by yc3 minus yc2. Okay, so, we have all the information just as we had for cell 1, we also have the information for cell 2. So, we multiply this by this plus this by this by this times this by this plus this times this plus this times this equal to the right hand side, which is nothing but C times the area of the cell. Okay. So, in this way we can simplify and get a similar equation for cell 2, and we have to do that for each of these things, and we will be able to get the 9 equations. So, in this tutorial we have seen how we can write an approximate form of the governing equation for a given cell, making use of the finite volume formulation of this. And this again gives us one set of equations, and the next lecture we will put down all the equations that we get from all the 9 cells, and then we can see how we can solve.